Next, chapter 6. Name of the chapter: Analysis of Stability by Root Locus. Subject: Control System Engineering, Semester 6, Branch Electrical, Faculty Aeronautic, Designation HOD Electrical. Root Locus Technique. In the root locus diagram, we can observe the path of the closed loop poles. Hence, we can identify the nature of the control systems. In these techniques, we will use an open loop transfer functions to know the stability of the closed loop control systems. Is basics of root locus. The root locus is the locus of the roots of the characteristics equation by varying system gain k from 0 to infinity. We know that the characteristics equation of the closed loop control system is 1 plus Gs into Hs is equal to 0. We can represent GSHS as GSHS is equal to K into Ns by ds, where K represents multiplying factor, Ns represents number of numerator terms having factored nth order polynomial of S, ds represents the denominator terms having factor mth order of the polynomial of S. Substitute GSHS value in the characteristic equations. 1 plus K into Ns by ds is equal to 0. ds is plus k, ns is equal to 0. Case 1, 1 minus k is equal to 0. If k is equal to 0, then ds is equal to 0. That means the closed loop poles are equal to open loop poles when k is 0. Case 2, minus k is equal to infinite. Rewrite the above equation, characteristic equation as k whole into 1 by k plus ns by ds is equal to 0. That will be 1 by k whole into ns by ds is equal to 0. Substitute k is equal to infinite in the above equations. 1 by infinite plus ns by ds is equal to 0. That implies ns by ds is equal to 0. That implies ns by is equal to 0. If k is equal to infinite, then ns is equal to 0. It means the closed loop poles are equal to open loop poles when k is infinite. From the above two cases, we can conclude that the root locus branches start at open loop poles and end at open loop zeros. Angle condition and magnitude conditions. The points on the root locus branches satisfy the angle conditions. So the angle condition is used to know whether the point exists on root locus branch or not. We can find the values of k for the point on the root locus branches by using magnitude conditions. So we can use the magnitude condition for the points, and this satisfy the angle conditions. The characteristic equation of closed loop control system is 1 plus Gs into Hs is equal to 0. Gs into Hs is equal to minus 1 plus J0. The phase angle of GSHS is angle of GSHS is equal to tan inverse of 0 by minus 1. That is equal to 2n plus 1 into pi. The angle condition is the point at which the angle of open loop transfer function is an odd multiple of 180 degree. The magnitude of GSHS is minus 1 square plus 0 square root over that is equal to 1. The root locus is a graphical representation in a S domain and it is symmetrical about real axis. Because the open loop poles and zeros exist in the S domain, having the values either as a real or as complex conjugate pairs. In this chapter, let us discuss how to construct or draw the root locus. Rules for construction of root locus. Follow these rules for constructing a root locus. Rule 1. Locate the open loop poles and zeros in the S-plane. Rule number 2. Find the number of root locus branches. We know that the root locus branches start at open loop poles and end at open loop zeros. So the number of root locus branches n is equal to number of finite open loop poles p or number of finite open loop zeros z, whichever is greater. Mathematically, we can write the number of root locus branches n as n is equal to p if p greater than z, n is equal to z if p less than z. Rule number 3. Identify and draw the real axis root locus branches. If the angle of open loop transfer functions at a point in an odd multiple of 180 degree then that point is on the root locus. If odd number of open loop poles and zeros exist to the left side of the point on the real axis, then that point is on the root locus branch. Therefore, the branch of points which satisfy this condition is the real axis of root locus branches. Rule number 4. Find the centroid and angle of asymptotes. If P is equal to Z, then all the root locus branches start at finite open loop poles and end at finite open loop zeros. If P greater than Z, then Z number of root locus branches start at finite open loop poles and end at finite open loop zeros, and P minus Z of the root locus branches start at infinity open loop poles and end at infinite open loop zeros. If P less than Z, then P number of root locus branches start at infinite open loop poles and end at infinite open loop zeros, and Z minus P number of root locus branches starts at infinite open loop poles and end at infinite open loop zeros. So, some of the root locus branches approach infinity. When P not equal to Z, asymptotes gives the direction of these root locus branches. The intersection point of asymptotes on the real axis is known as centroid. We can calculate the centroid alpha by using this formula. Alpha is equal to summation of real part of infinite open loop poles minus summation of real part of infinite open loop zeros divided by P minus Z. The formula for the angle of asymptote theta is equal to 2q plus 1 into 180 degree by P minus Z, where q is equal to 0, 1, 2 up to P minus Z minus 1. Rule number 5.